yeah, today I'm going to talk about computer vision and basically just introduction to it, so no hardcore stuff. First, a little bit about me. So I'm a long-time Python enthusiast, like for, I don't know, 5, 6, maybe 7 years. I recently graduated from the university in Germany, and throughout my academia life, I was focusing on things like machine learning and essentially computer vision. So yeah, currently I work as a backend and algorithm engineer, and you might be curious what's this thing in my head, and this is something for visual odometry, and I'm going to talk about it towards the end of the presentation. So like, why computer vision? Like, it's getting more and more popularity last years, and there are a lot of different viral projects. Like, maybe you've seen this one. This is a project by Microsoft, and what it did, it tried to take the image of the person, find the face, and then predict the age of the person. And sometimes it worked, and sometimes it didn't, and there were quite a lot of hilarious pictures in the social networks. But what it helped is, what was the outcome is that it popularized computer vision. Maybe you've seen these things. These are some augmented lenses for your face, and again, it's not something in the lab or in the university. It's something that regular people are using. So computer vision is getting more and more spread throughout the community. So there are a lot of different things in there. Like, maybe you've heard about image classification. That's when we have some image and we try to say what's in there. And there was a big breakthrough in 2012 by Alex Krzyzewski and his team, where they first successfully used convolutional neural networks and deep neural networks. And there is a harder task of object recognition. So instead of classifying the whole image, there are multiple objects in the image, and first we have to find these, and then we can classify them. There are things like odometry, where we try to figure out the position without using of GPS or any other location system, where we only use cameras or IMUs. We can also build dense maps of the surroundings. And also we can build some 3D models of the objects just by using photos from different viewpoints. So what am I going to talk about today is just a few methods, a few quite basic methods from computer vision, and how they work, but kind of briefly. So I'm going to talk about like what images are usually used, how to detect edges and lines, what are descriptors, and some other things. And I will also talk a little bit about my research, so to give you guys some practical example of tasks from computer vision. There will be no neural networks here, so. So first, like, the easiest unit in computer vision are binary images. So binary images are just metrics of 0 and 1s. This is an example. It's the simplest case, and we can use it to distinguish foreground and background. And then, like, right next to it goes grayscale images. It's more complicated in the sense that instead of 0 and 1s, we have now float values. So yeah, every pixel can be from 0 to 1, or it can be from 0 to 255. It depends on the implementation. And because there are much more options of color, I mean, not color intensity, it captures much more of the variance of the object. And like, I'm not going to talk a lot about color images here, because core methods in computer vision, they usually just work with grayscale, so it's sufficient enough. And first operation we can do is, how do we convert from grayscale to binary? And this is an operation called thresholding, which is very easy. Yeah, so that's the formula. It's not scary at all. So we just basically make some threshold t, and if some pixel value is greater than t, then it's 1, otherwise it's 0. And how do we pick t? So we can use domain knowledge. So for example, we worked with some grayscale images before, and we know that for which value to pick. Or there are different mathematical methods that allow us to find the t through the computations and through the color distributions, but I'm not going to talk about it now. I'm not going to show a lot of code here. It's more like algorithms and math, but just to give you a taste of how easy it actually is. So suppose we want to threshold an image. So we import some libraries, then we load the image, we can display it. And this is a thresholding. And like there are in total like, I don't know, 8 lines of code. And thresholding essentially is just this line. So because how easy is Python and how high level it is, we can abstract operations like this easy. And here 120 is at some threshold. However, there are problems. Suppose you have a scan of the page with some text and we want to basically binarize this image thresholded. But if we just use some even good threshold, we will end up with a situation like this on the right, where as you see, the lighting is different in 2 parts of the image. So here it affects the result and the left part is just unreadable. So there is a solution. Instead of using a global threshold for the whole image, we can use some local window, go through the whole image, and then calculate threshold separately for every image using some normal distribution of intensity. It's called a Niblack thresholding, and this is a result of applying it. So you see, instead of having some black part here, which is unreadable, here we have a nice binarization of the image, and we can read the whole text. Now moving further, I'd like to talk about edge detector. So basically the idea is that we want to get the outlines of the objects, which are called edges. So for the photo on the left, we want to get something like photo on the right. Here we already start using some math. Did someone heard about Gaussians? No? Okay, good. Do you know about filtering or convolutions? Okay, still good. So basically what we do is we filter image with Gaussian derivatives, but instead it's a bit complex, so instead we use just approximation, which is just these 2 matrices. These are 2 derivatives in different directions, x and y. And this gives us how much the color changes between neighboring pixels, how much intensity changes between neighboring pixels. And if we take if we take the square root of these 2, then we get basically the intensity change in both directions, which is called the gradient magnitude. And this is what we get. So you see, it already looks like edges a little bit. So it looks like maybe what we want to have. But it's not that easy. Yeah, so we use magnitude for this. Simple idea that we can think about is, why don't we just threshold this? Like we already know how to do it, and it's a very simple operation. But unfortunately, it doesn't work well. So is it visible? The line in the center is actually thicker than here. It's not really visible. Yeah, so if we just do the thresholding, we can have this part, but these parts of the line will be lost. And it's not what we want. We want to have the whole line. So instead, there's a Canny edge detector where we have 2 thresholds. One is called a stronger one, and one is a weaker one. So the algorithm is that first we pick a strong threshold, and we just threshold these grade magnitudes. Then we have only like this part, for example, and these are lost due to thresholding. But then we look at the original black and white image, and we try to filter it with weaker threshold. And we try to continue strong parts to the weak parts. So instead of like, if this part would be somewhere isolated, it would be lost. But since it's a part of a strong edge, it will be preserved, and we will have this whole edge together. So this is like improvement of just regular thresholding. And again, just to show the pipeline, so we have original grayscale image, which get filtered by Gaussian derivatives, and we have this. And then we use Canny method, and we receive edges in that. So it's not that complicated. So this is another example of the application where we have some engine parts and we try to get edges from there. So naturally, next step we want to take after detecting edges is to detect lines. Lines get a bit more complicated. So why not we just use edges, like we already have them? Edges are still noisy. So you see here, like we don't have a straight line. We have some noisy part, and here again, and there are some parts. There are some extra points, which are not actually part of the line. So you see some noise here. I don't know why it lags. And some parts can be missing. So if we have a look here, like this is a line, and obviously it continues here. We can't have built-in hanging in the air, but it's not here, so we can just use edge for this. So there's a method called Hough transform, which is a voting technique, and we just try to see, okay, for this particular point of the edge, which lines can be fit, and we just do it for all points. So here we have more math. So who remembers something from the high school math? Okay, that's reassuring. So you might remember that if we have some line, and we have here image space, like so we have some line in the image. This line can be parameterized by this equation, because it's a linear line. Yeah, linear line. And here we have another space, let's call it Hough space, where for each line we have a point. So we just take this A and B and just put a point in here. So far so good. Yeah. Suppose we have another line which has different parameters, and then it also produces a point in the Hough space. So for every line in the image space, we can have a unique point in the Hough space. That was me when I was first learning this. Now let's try the other way around. It appears that for each point in the image space, we have a line in the Hough space. So you see, line here, point there, line there. Yeah, and if we have more points, we have more lines. And the nice property of this whole technique is that if our points lay on kind of a line, then lines here would intersect. And the intersection, like this point, if we project it back, then it results in the line in the original image. So basically that's whole Hough transform technique. We go for every edge point in the image space, we build a line in the Hough space, and then we just look for strong intersection and transfer line back. And then we have a line in the original image. Yeah, I know it sounds maybe a bit complicated, but like if you would be interested in topic and try to dive deeper, like it's not that complex. And however, like we don't use this AEX plus B representation. Usually this polar representation is used just for some numerical reasons. And instead of lines in Hough space, we have some weird arcs. You'll see now. So suppose we have some image. And we have some edges that we extracted by Canny edge detector. And this is how Hough space looks for this image. So do you remember I said that instead of lines, we have these weird arcs? That's due to polar representation. But the idea is completely the same. We try to find points of strong intersections. And then we extract lines and project them back to the original image. And we have all these nice lines fit to chalkboard. And we can now use it for calibrate cameras and for lots of stuff. Okay, so we are done with lines and edges. Now I'm going to talk about descriptors. So there are two kinds of descriptors, global and local. And first, global. So the idea of global descriptors is how do we compare images? How do we say that images are similar? So this is the example. I took some image from the internet and put it to Google Images, and that's the result I receive. And you can already see that There's one striking similarity between them is color. So there's a bit of yellow in the middle, and it's more dark and gray on the background. So how do we compare images? One obvious idea is to compare them pixel by pixel. But it's actually a terrible idea, because even if our object is moved by a centimeter, then it's already a different image because pixels have changed. It's not robust to anything, to noise, lighting, position change, so bad idea. So there are multiple global descriptors, but one of them is let's capture color statistics, because as we have seen, similar images have similar color distributions. So we just built 3D color histograms. 3D color histogram is just a regular histogram, but in 3D and made out of color. So because we have RGB, and we can build this over 3 axes. And it works surprisingly well. So here we can see that these are the same object, but parts are missing, and it's also moved, and it's turned around. But if we look at the histograms, even by naked eye, we can already see that it looks quite kind of similar. So we can assume that this is the same object. We also need a way to compare histograms. I'm not going to talk about it. There are multiple methods, and you can check them out. Yeah. However, it's still not good enough. When we compare images globally, they're still prone to illumination changes, object pose changes, clutter, occlusions, a lot of things. So you see here we have the same animal, but if we just try to use colors to compare the images, we would fail because the colors can be various. And it goes further. So this is the same sculpture, but again, the crop is different and the lighting is a little bit different. Color statistics will not help here, probably. It's even worse here, because the viewpoint is different. And I like this example. So does someone see the match between these two images? No? So actually, it's not bright here, but these rocks and these rocks, they're actually the same rocks. But again, color will not help us here. So we are slightly coming to local descriptors. Another topic is panorama stitching. So you can move your phone around, and you get one wide picture, and it actually makes a lot of photos and then just stitch them together. So we need to stitch the photos. We need the way to find points that are similar. Not the whole images, because we moved the camera, but just points in these images. And this thing, it should be repeatable. So if we make 2 slightly different photos, the same points should be detected. And it should be distinctive. So, okay, the same points are detected, but how do we compare them? And how do we know which one is which? So first part is how to get key points, which are basically pixel coordinates in the image that are reliably detected throughout different photos. So scientific community find out that actually corners are very good key points, because if you have some flat region, there's no information change when we move it. On the edges, it's basically the same. You can move it up and down, but corner, it's very distinct. If you move the patch a little bit to any direction, you already get a different picture. So it's repeatable. If you even move the camera, the corners are still there. It's distinctive. We'll talk about it later. And corners are easy to find computationally. So there's a thing called Hessian detector, which takes second derivatives over image. So we were using first derivatives. Here it gets worse. It's second derivatives. We build the metrics, and then we calculate its determinant. And that's it. The stronger is determinant for some pixel, the higher probability that there's a corner there. So this way we can find corners in the image fast, easy, and reliable. So now we have these pixel coordinates. But how do we compare pixel coordinates? You can't compare pixel coordinates. You need to compare something around them. And that's where local descriptors come. Yeah. So there are multiple of them again, but I'm going just to talk about one of the most popular ones, which is SIFT, or Scale Invariant Feature Transform. It sounds scary, and it is scary. Here is a brief idea of how it works. But if we talk about it quickly, so it's just we take a patch around a key point that we found edge on. So suppose we found this edge. Then we split it into parts, and then we get the orientation of the color intensity changes. So, and build histograms out of them. Just try to figure out which angle is the most frequent, for example. And then we stitch it together in a single vector, and that's it. This way we can compare patches around key points. And this descriptor turned out to be very good. It's very robust to elimination changes, it's fast, and it's basically, you can find it everywhere in computer vision. It's state of the art. And the example when it works well, you can see, like, you remember this sculpture? So this is some selfie, and it can detect similar points between these two images, which is very challenging because we have completely different viewport, we have clutter, we have people, and we have different color. So it works very well. I'm actually going faster than I expected. So next technique I'm going to talk about, it's a little bit from machine learning, but computer vision has a big overlap with machine learning. It's called AdaBoost. Yeah, it's classifier, and it's not just like a simple classifier, like, I don't know, sigmoid or something. It's a combination of lots of classifiers. And these are weak classifiers, and they are called weak because they're not good. They are correct just in slightly higher than 50% of cases. So like maybe 52% of cases, it's already good enough. But we have lots of them, like hundreds or thousands. And then we can calculate the weights for the classifiers and combine them into one big, strong classifier. Yeah, so suppose we have some points, we build some not very correct classifier. And then for the second time, we just increase the weights of the points that were not classified correctly. So there's higher chance they will be classified correctly later. Yeah, and we have more of this. And in the end, like having a lot of classifiers and their weights, we just take a sum of them, which is just simple linear combination. So we have a big classifier built out of smaller ones. And why am I talking about this? Because this approach is used in Viola-Jones detector. Viola-Jones is used to detect objects, and it's also very popular for detecting of faces. And you remember, we have just a weak classifiers. Yeah. So how it works is it takes a lot of these integral filters, which just say, okay, take the value of these pixels and subtract values of these pixels in this region. And there are a lot of them, and they usually just randomly get generated, so all possible options. Yeah, so it looks like this. For every position, for every rotation, we generate a lot of these things. And they are very weak classifiers by itself. Like, you can't classify face by using like Ukrainian flag in here, like it just doesn't work. But since we have thousands of them, and even hundreds of thousands, it actually works quite well. So if we combine a lot of these classifiers, we can detect faces easily. Yeah, just an example of this. Okay, so I've talked about some methods. Like, this is just tip of the iceberg. So computer vision is quite a big science, I would say. And there are interesting things like classification using deep neural networks. So everyone is talking about neural networks today. It's really used a lot. There are things like odometry, where you detect your position, and I'm going to show some examples now. There is stereo vision, and the nice, or not nice thing about stereo vision, that there's a separate geometry for this. It's called epipolar geometry. And once you get into it, it's really interesting. And there are things like object tracking. Okay, so now I'm going to talk about what I have done, like some projects of mine. This was my master thesis. So it's called Visual-inertial odometry. And here visual means that we use cameras. Inertial means we use an inertial device, which is called IMU, you know, this accelerometer and gyroscope, you have them on your phone. And odometry, this is from robotics, this term, and it means we try to detect location. So yes, we can try to detect the location of the camera and of our whole setup or robot somewhere where there's no GPS or no nothing. And examples include, like, I don't know, Mars. So Curiosity uses this technology. And this is the cameras we use. So this is basically a photo of what we have assembled. So there are two cameras, and there's an inertial measurement unit here. And it was kind of hard because we have to calibrate them all separately and then all together. So in computer vision, the task of calibration is actually quite a big one. We spent like a month for this. And it was attached to a laptop, and then you can walk with it. Or what we did, it was mounted on my bicycle. So I could just, go around and take turns around the campus recording things. And I was also walking with it like this for 20 minutes, making circles, and people were looking weird at me because I had like lots of wires going in here. Yeah, so it used in Mars. And for example, these Roombas, home robots, like last generation, they used the same technique to detect their position in the room. Because like they are placed in new rooms every time, and they need to build a map somehow. Yeah, so that's me. And these are wires, and there's a laptop in here. And this is a video. So on the right side, you can see the frame of the camera, and this is not important. And here you can see the path that is being built. So here there are two methods, the one that works in local window and the one that works in the global scale of the whole map. And here blue one is the local one, and red one is the global one. So red one always lags a little bit. So yeah, it tries to detect the location in their relation to the original position, because we don't have any absolute coordinates, we just have some relative coordinates. I'm not too sure if I have any impact on it. Yeah, so it was a nice and interesting project, very challenging one. I used Python, and C++, but more C++ than Python. But I think it's still good enough to talk about PyCon. Yeah, so you can see now the result of global constraints. So you see so far these two methods, they deliver basically the same position. But I'm making a loop here on purpose. And once the algorithm detects that I've been here before, it corrects the path. And like basically it returns me to the point where I've been before. Yeah, so in the end you can see that like we tried to return here, which was the original location, but we are still quite off both methods. But since again I'm making loops in here on purpose to test my algorithm, it now detects it and closes the loop, and we basically in the end we return almost to I think the final error is like less than 1 meter, and this whole track, its length almost 2 kilometers. So 1 meter per 2 kilometers, it's a good accuracy actually. And again, no GPS or anything was used, only cameras and inertial measurement unit. So in case someone is interested, there's a paper about this. You can read it. I will post the link. The link to the slides is on my website. There's a link to my website in the end. So okay, now about Python, because it's a PyCon. So how we do all of this in Python? There are multiple libraries. So these are, like, I would say, most famous one. So SciPy and NumPy, you can use them for some low-level stuff. Scikit-image is a very nice and very Pythonic library to manipulate images. There are like functions and methods for all the algorithms that I was talking about. There's also OpenCV. There's binding from Python to C++, which is like less Pythonic, obviously, but it's very popular and very powerful library. And some examples using OpenCV. So you remember Canny edge detector? That's how you do it in Python. It's just one line. How we detect lines? Again, one line. SIFT, it's more complex. We need 2 lines for that. So we first, okay, you can actually put it into a single line, yeah. So you just create the descriptor, and then you say detect and compute, and it detects and computes, and you receive key points and also these patches around them, the descriptors, and then you can compare them. Okay, so that's basically everything I wanted to tell about, so I would like to answer your questions.
Hello. What is the role of the second camera in your device?
Sorry?
What's the role of the camera in your device?
Okay, so we want to look for the points in the world, and when we move our cameras, we want to see where we have moved in the relation to these points. So we can use one camera for this, but the problem is that we have depth ambiguity. So having only one camera, you don't know how far points are from you. So they can be very close or they can be very far. You don't know if you have only one camera. So for this, we have 2 cameras, which are calibrated, and then we use this fancy thing called epipolar geometry, and you can triangulate the point in the world in metric scale. So we know, okay, this point is like 3 meters from us. And if we move a little bit, okay, we moved like 10 centimeters or whatever. So there are approaches to this problem with using only one camera, but they do not deliver metric scale. So they only deliver relative scale, relative trajectory.
I have a question. How many square meters you covered when you tested your coordination system, and how much data need to, I don't know, to cover with all this photo to for some small city?
Mm-hmm. Okay, so when I was testing it, I recorded like, I don't know, 6 data sets outdoors, and everyone was around 2 kilometers, so it was a nice working out. Also, I recorded like 3 kilometers by bike, but we did it only once because it was very scary, because if I fell or if some car comes in front of me, and this whole thing costs a few €1,000, so yeah. For the city, I mean, you just, I guess you have to cover all the main streets, so it depends on the length of them. Just smaller the city, the less you have to cover. Okay, so the storage, it highly depends on your frame rate and the number of cameras and the resolution. So we had 2 cameras and the frame rate was 20 frames per second. So this, like 1-2 kilometer walk, I think it was like 30 gigabytes or something, maybe 40. But if you want to cover the city, then obviously it will be much, much bigger. There are guys who were doing experiments and they were going by car, And they were covering like hundreds of kilometers, so I can only imagine how big of a data set they had.
May I ask a question? Okay. So I wanted to ask a question. You described the process of figuring out what's in that image on a static, like on a static image, and then you kind of jump to the dynamics of changing images, and where this magic happens. It's interesting, like, because you add another dimension, which is time, and it should give you a lot of information about, like, you don't have some information in one frame, and the second frame you get more information. You need to be able to use this. And how does this happen?
So there are different approaches. There are people who use Kalman filters for this, but I personally never did this. So our approach, we built a graph, kind of. So every frame, it was some entry in the graph with some parameters that can be estimated. And then there was a next frame connected to this one. So we basically had some local constraints, like parameters, and then we had some constraints between neighboring images. And then you put it all together into Optimizer, and it delivers you the best result. So that's where it works. And there are lots of techniques. There's a thing called structure from motion. I think it also implies to what I'm talking about. That's, again, it's used in the movies to determine some 3D positions, so you can then build 3D models in them. Yeah, but it's, of course, more complicated than just use a simple single image.
So, thank you. Thank you. I have a question about SLAM. How do you recalculate the path after you close the loop?
Okay, good question. So there are multiple approaches. I used one. It's called DBOV, which doesn't tell anything, but it's just how it's called. And basically it build an index of the images that you have seen. I think it uses image vocabularies and inverted vocabularies. So it tries to find some distinct points and then see, okay, have we seen these points before? And if yes, in which images? And if there is a big enough number of points seen in similar images, then we know that these images look similar. Yeah, kind of like this. So if you want to have a look, it's DBOW. Yeah, I keep the images for the whole path, and I keep a global graph. And if I find some matches, then I add extra constraints to the graph, and it re-optimizes everything. So there are obviously advantages and disadvantages of this approach. So local approach is faster, and it requires less memory because it just keeps few last frames. And global approach, you can have its advantages when you see the loop is closing, so we can incorporate it.
And so the question is that you explained the 2D, like 2D example, really good, and the results are pretty impressive. But the question is, if you have tried any experiments in 3D space, so.
What
I
like
mean,
my approach, it delivers 3D coordinates.
3D, so I understand it's 3D coordinates, but you just, in your case, you just were working on.
No, it was like.
So exactly the topography of the landscape was also captured. Yes. Okay.
I don't have an image here, but if you go to my paper, there are plots of z-axis throughout the path.
Any other questions?
Thanks.